Welcome everyone. I would like to say hi to all of you who join our live stream today. My name is Janeta, and I am responsible for human resources and employer branding here at Sunscrapers. So I would like just to say you a few words about our company before we start, just to let you know who is talking to you here. So we are a dev shop who creates mobile and web apps for clients around the world. But we are also huge fans of supporting community. That's why we are sharing this presentation with you guys. We also support some events in Warsaw like Dev Heroes, PyVav, or Pilot. And I'm talking about that today because Pilot is just in a few hours. It's 6:30 today in Hala Koszeki. So for those of you who are in Warsaw, you can join there for free. Or if you are in a different city or you don't have time, you can also join Pilot streaming. You can find it on Pilot Facebook page. Okay, so something more about our today tech talk. If you would have any questions during that presentation, you can just type them on YouTube chat, and Paweł will answer all of them after the presentation. And today's topic is about Julia language, and our presenter is Paweł, our backend developer. So I think we are ready. We can start. So here we go, Paweł.
So, hello. Today's presentation is about Julia, as Janeta said. This is the quickest introduction to Julia. I don't claim it to be really the quickest, but it will be like it will cover only basics, and it's for Pythonistas because I'm a Pythonista myself, and I can compare those two languages. I don't know MATLAB, for example, so from this point of view, I won't be able to compare. So yes, this notebook, it's in the IPython notebook or Jupyter notebook. It can be found on my GitHub. I created a gist. So let's begin. What is Julia and why should I care? So Julia is a fast, easy to learn, quick to prototype with, and a free language. So it's fast, almost like C, not like Python. It's easy to learn and quick to prototype with, like Python, not like C. And it's free, like basically every programming language, unlike MATLAB and Mathematica. I was told that MATLAB is very expensive, so I think the Julia really hits the spot here. It's designed to perform high performance numerical and scientific computing. It's fast. It has just-in-time compiler and very smart type system, which helps compiler to optimize the code. Programmer needs to know about the type system to utilize the compiler or the compiler capabilities, but it's not that hard. Also, Julia has a very powerful meta-programming capabilities, which I won't talk about. I also want to talk about type system here. What I will talk about is basic types, syntax, defining functions, control flow, arrays and indexing. And I will cover, because this is for Pythonistas, I will cover calling Python modules from Julia code, which is surprisingly easy. So let's begin. First, let's see just-in-time compiler in action. Just-in-time compiler, I won't get into details, but it works like when I first run the function, the compiler figures out how the function is running and optimizes the compiled code for this function and for its arguments. So let's define basic function, and let's run it for 2 integers. So as we can see, it took some time and some memory. So let's run it again on also 2 integers and other integers to be sure it's not cached or anything. So as we can see, it's really faster, and it took really little memory compared to the first one. So let's now run it on 2 floating point numbers. So it's slower than on integers on the first call, and also it took some memory. Let's run it again. Oh, it's really fast. So right now I can run this function like one more time with some other let's add time, not a decorator per se, but it's similar syntax to Python. It's a macro, it's a metaprogramming thing this time, but let's see. Wow, it's still fast. We can also try to run it on integer and float. Oh, it's slow again. But what if I, sorry, let's make it pretty again. What if I call it with integer and another float again? Oh, it's fast. So compiler specializes for specific types. Every time it runs, and the compile code is really fast. The next time I run it. Yes. Yeah, here is I run this cell twice. That's why it's fast. It should be. Yeah, but I won't reset the kernel for this. Okay, so let's see. Let's have a quick interview of basic types. I want to get into type system, but we need to know what we are dealing with. So integer. This is 64-bit integer. Yeah, nothing fancy here. Floating point, 64-bit floating point. Here, what is it? Is this a type operation? What happened? Let's add 2 to this. Right. Maybe now we can. Yeah, it's a rational number with numerator and then denominator. This is a really nice syntax of Julia. Rational numbers or fractions are really nice to deal with. We can use the function denominator and numerator to see those, and also we can do some math. Sorry, some math or on those. We can also use denominator with 0, and it works. So we can add 10, and it's still infinity. So comparing to Python, in Python the code would look like this. So first we import fraction, then we create fraction object with 2 parameters or 1 parameter with this syntax. This is equivalent, and it works exactly the same, but we don't have the nice syntax of 2 slashes. And we also can get denominator, denominator. We can do some operations, but we can't divide by 0. I mean, we can't have a denominator of 0. It's like, no. Python says no. Okay, so let's go to strings and chars. We have basic string type. It's Unicode. It works. It's fine. Yeah. Also, we have chars types. So it says that it's Q, it's Unicode, it's letter, and it's lowercase. So we have additional information about it as well. It's a char. Unlike in Python, indexing strings returns characters. So when we index the string hello there, we have L letter. We can check the type. Yeah, it's char. In Python, it's different. And Python is special in this case. When we index a string, we don't get we get a single letter, but this is not another type. This is not a character. This is a substring of the initial string, so we can do something like this, which looks silly, but that's how Python works, and we are used to it, and it's not problematic, but it's different. So yeah, let's go to some other syntactic things, or syntax per se. Julia uses one-based indexing. This is, from one point of view, small, from another, very big difference between Python and Julia, and between Julia and most of the modern programming languages. MATLAB, Mathematica, or Fortran use one-based indexing as well, and I don't know any language or widely used language that use it as well. Maybe some arcane ones do it. So let's define a string. Let's access to the zeroth index. Nope, it's not possible. We have bounce error. We don't have zeroth index. We have first index, and this is the first element. This will be the letter A. We can also access the last element. It's also different than in Python. We use AND keyword, and now we have G because this is the last element. Also, we can access second from the AND, and this is F because F is this. So it's intuitive and it works. Slicing. We can use this notation to get slices of strings. So those are first three letters, and those will be from the second letter to the end -1. So it's B, C, D, E, F. Nothing surprising here. We can also use start, step, stop syntax. In Python is when we define range, we have start, stop, step, and this is start, step, stop. So we need to get used to it. So now we will get first, third, fifth, and seventh letter. So yeah, this indexing, that one-based indexing, that really needs programmer needs to like get used to it, and it's not a problem when you are dealing with Julia all the time. But if you are switching languages, it can be really problematic for programmer to like switch a few times a day, for instance. So, but yeah, as I said, MATLAB uses the syntax, and I think it's the main reason that it's used here, because many things from MATLAB are taken into Julia. So, okay, let's define some functions. First, standard notation, we already seen that. Adding numbers, it works. So, unlike Python, return keyword is optional. Last expression gets returned, but we need to use return keyword to return immediately, to return like in if condition or in a loop. We want to stop functions from running and return immediately. And also indentation is optional, not only in functions but generally in Julia. We don't need any indentation really. We need only one white space, or even not that. The end keyword defines end of blocks. So this very function we can define with like this, without indentation and without return keyword. So it's less readable. I think using indentation is very it's a good idea generally, because we can really write messy functions without it, but we don't need it for the program to run, and interpreter or compiler doesn't care about it. So next one is math-like notation. We can define functions like this. For simple arithmetic functions, it's really great, and it works just like that. We're defining function name parameters equals, and then body of the function. And we can also use anonymous functions. So this is an anonymous function with 2 parameters, and return value is adding them together. We can use inline, anonymous function inline, but we can also assign it to a name, and it works. So basically, we have three types of defining functions: standard notation, this math-like notation, as I named it, and assigning anonymous functions. So the third one is not very smart when you have this math-like notation, which is nicer, I think, more readable. Okay, so now something interesting. This plus and other operators are functions also, and they are like really functions. We can do something like this. Let's comment this out to make sure that this one is returned. Yeah. So when we use this notation, we can see that plus is a function really, and plus and other operators can be passed around. So maybe let's do this like this. So let's define silly apply that takes a function, 2 arguments, and you calls this function with those arguments, and call it with plus and 1 and 2. So 1 will be applied, 1 and 2 will be applied to plus. So yeah, it works. We can do it just like that. In Python, we would have to import special plus functions or add function from standard library. So this is more convenient. Also, other operators can be used here as well, like minus or like division. Yeah, it works. Okay, in Julia we have a very nice convention, smart one. If a function name ends with a bang, exclamation mark, we know it may mutate its arguments, or it does mutate its arguments. So let's define an array. We will get into arrays in a second, but let's assume we know what that is. Those are like lists, but not really. So this is an array, and we are using built-in function reverse without exclamation point, without a bang. So it will return an array without modifying it. Okay, so it's now reversed from 7 to 1. Let's make sure it's not modified. Yep, it's not modified. It's from 1 to 7. But now let's call reverse with a bang. It also returned this array, but also it changed it in place. This is an array, and the initial array was changed, mutated. So this is one of those tiny things that are really, really helpful if you know how to use them, because if you define your own functions, you should also use this convention, and this is only a convention. Compiler does not check it. Okay, so now let's see how control flow works in Julia. So yeah, let's define some silly function. Let's see how big is x. If it's smaller than 2, it's little. If it's like bigger than equal to 2 or bigger than and smaller than 7, it's pretty small. But if it's less than 20, we can say it's medium, and so on. So like this is silly function. As you can see, we use if, else, and then end, and the end of the if statement block, not statement, if expression, because as we will see, conditionals are expressions, not statements. So let's check how big is 1. 1 is little. How big is 99? 99 is big. It's not huge, but it's big. We can check if 101 is huge. Yeah. Okay. Also, I used here string interpolation, which we have in Python 3.6 or 3.5, I don't remember. But the syntax is different, but it works. It works the same. So as I said, if, else, and blocks are expressions, they return a value. And as the doc state, this value is simply the return value of the last executed element in the branch that was chosen. By branch means that part of the block that was that is chosen by the conditions. So what this function will do? This function, is it 1, checks if parameter x is 1. We store the answer in answer name and check if x is 1. We print that it equals 1, and we write true. What does it mean? This is the last executed statement in the branch, in this branch, and else it's the number doesn't equal 1, and we return false. So this whole block, starting from if and ending in end, will return a value, true or false, and it will create a side effect of printing a string. And then we will return the answer. We could have also put the return instead of answer, but this way we can see that it's really returned. I mean, we would see either way, but so we have, is it 1? It's 25 1. No, 25 doesn't equal 1. And this is printed, and this is returned. Yeah, it's as simple as that, but we can have also 1 and be happy. Next up are for loops. For loops are defined like this. So with for something and we use this notation of item that is used to iterate over, and the collection that is iterated over. So yeah, it works like this. Equal can be replaced with in, just like in Python. So no surprises here. Also, we can do something like this, but what is this 1:6 thingy? This is a range object. We have a range objects in Python, similar ones, which represent, or the generators that generate values from 1 to 15 in this case. It's unit range of integers. So in this type, we already have information about what does this range produce. We can also check if something is part of the range. The range must be, of course, iterated over to check it. I'm pretty sure it does, because there may be a. I mean, I didn't check it, so yeah, but we can do it. And we can also access ranges by indexing them. And we can also use start, step, stop syntax as the similar or the same, really, as we've seen in ranges. So it will iterate over numbers from -10 to 11. Every free number will be returned by this range. Okay, let's go to arrays. Array is the most basic and very powerful Julia's collection type. It's basically based on MATLAB. So the easiest way to define an array is to do it like this. This is a syntax that it's very similar or the same as syntax of defining lists in Python, but arrays are different, as we will see. So this is a 4-element array of 46-bit integers with 1. This 1 means that this is a one-dimensional array. Let's double check. Yeah, this is an array of 64-bit integers, and it has one dimension. This little one points this. Yeah, so we can check size, use the size to return the dimensions of the array. So we only have one dimension because this is one-dimensional array, and this dimension has a size of 4. Also, we can use this notation. This is different. We are not using commas. So what changed? Now we defined a two-dimensional array with only one row. So let's, yeah, we have confirmation that this is array of 1 by 3. Already we've seen it here. It's 1 by 3 array. So right now it's the difference between those two arrays is not like something important, but when we have more dimensions, we'll see that it makes sense. So let's define a 2D array, 3 by 4. To create new rows, we use semicolon. So this is a 3 by 4 array, which is two-dimensional. This 2 means that this is 2D array. And let's double check. 3 by 4, it works. So yes, arrays, 2D arrays are not array of arrays. Like in Python, we probably would have, I mean plain Python without NumPy and other things. This is plain Julia, yes. So we can in Julia create arrays of arrays, but most of the times it's not what we need, or not what we want. Arrays are for our basic types, so and they support dimensions. So and dimension is a parameter of every particular array's type, because this array has different type than this array, yes, because this array is two-dimensional, and this is this array from that array, because this is one-dimensional and this is two-dimensional. So those have different types. Okay, so let's create 3D array using function zeros, which will create array filled with zeros in the shape of S as its parameter. We can. So let's create an array of shape 3, 3, 3. That looks like this. It's filled with zeros, so it's not useful for us right now. I mean, it may be. We can fill it with some significant things, but so yeah, this is a MATLAB notation for arrays. I mean this column. So yeah, this is the whole array. So those are like slices of array. This is the first slice, this is the second, and this is the third one. So this is like x-axis, y-axis, and those are like z-axis. So yeah, we can also create for the array using function once, because we have also function once that creates an array in the shape of parameter, which is 2, 2, 2, 2, and we have for the array, which is, yeah, looks like this. And we can also create a, let's create an array of, like this, crazy, yes. 6-dimensional array. Okay. It's pretty big, as we can see. So yeah, but we can do this. Okay, let's get rid of it. How do we index over arrays? We have two basic indexing methods. First is linear indexing, and this is, let's see how array 3 looks like. We can access elements of this array by linear indexing. That is by one number in square bracket. So first one is 1. Second one, can you guess? I think you didn't guess, because natural way of thinking about it, it's that it's the 2 is the second one. Maybe a MATLAB programmer would guess Yeah, the second one is 5. So the third one is, of course, 9, and the fourth one is 2, because it goes from columns first. Also end. So 12 is end of this array. So we can access indexes in a linear way, which it's mapped on the array. So when we iterate over the array using, for instance, for loop in a linear way, so just like this, we'll get the whole array. And it doesn't matter if it's 3D array or 10D array. It works for on every array. But also we can use Cartesian indexing, that is using Cartesian coordinates. We can specify for the 2D array, we can specify a row and column, and for more generally, we can specify all the axes, all the coordinates on all the axes with this notation. So let's see, array 3 looks like this. So now we access first element from we access first row and second column. First row is this, second column is this. So I hope we will get 2. Yeah, we get 2. Also, we can use this syntax, colon syntax, to select whole dimension. So right now we will select first row and and the second dimension are all columns. So we'll have, the other way around. It's confusing because it changed direction, but yeah, it's exactly as I said. And the other way around, we can select whole row of second column. Whole column of this, every row of second column. This is proper way to describe it. And every time we get a one-dimensional array, so we can, of course, do other operations on those arrays. So now let's create, using Reshape and collect functions, let's create an array of 3 dimensions. Reshape function, collect function iterates over an object and it creates an array out of it. Maybe I should do something like this. Yeah. So this gets the elements out of the range object and creates an array out of them. In Python, we would do something like list range 5. Yes, but this is named collect. I don't know why. And Reshape creates reshapes an array using dimensions provided. So now we are out of one-dimensional 27 element array. We are doing 3 by 3 by 3 3D array and assigning it to array 6 name. So it looks like this. This is 3D array with 3 dimensions and with unique numbers. It will be easier for us to see how selecting parts of this array works. So using the Cartesian coordinates, we can select first element from first row, first row, third column, and second slice, let's call it, and it's 16. It's here. We can select whole first dimension and second and first column and second slice. It's 3-element array. We can also choose 2 dimensions and specify only the third one. So now we get 3D array. We can also do every combination we please. So it's really, yeah. We can also do something like this, array 6, and select all the dimensions. It's silly because it's like typing array 6, but it works. We can also use slicing with Cartesian coordinates. So let's create an array 4x4, and we can use slicing to select parts of this array. So this will select first and second row, and first and second column. So it's not surprising that it took this bit from this array, and we can also select other parts with this notation. Okay, arrays can be mutated, as we saw, and mutation can be done in both ways using linear indexing. So array 6 looks like this. We can assign 9,999, whatever, something to 4th element, and let's see, up is there. And we can also use Cartesian indexing let's see the array 6 one more time, and we are now assigning 1 1 1 1 1 1 1 1 1 to first row, second column, and third slice, and it will look like this. It's here, so it works. And also we can mutate using slices. So array 7 now looks like this, and now let's select a slice of this array and assign this array to this slice. So this array, it's put in this part of the array 7. So yeah, it works like this. Like in Python, we have comprehensions. So basic syntax looks like this. Nothing fancy, but very helpful. We can also use iterate over many items in comprehension, similarly in Python. So we can produce 2D array out of 2 ranges, and we can also make fun with that. As you can see, you can use Unicode emojis to have fun, and we have this array. Yeah, it works. So right. Those are the basics of Julia I wanted you to know. Now there is a part of calling Python code in Julia. I will show the basic example. Let's say in Julia we don't have a request library. I mean, we do, but something similar I'm pretty sure that there is one. But let's say that we don't have. So in Python, we would import requests. Let's say get some address, check response, check status code of this response, check headers, and everything works. But in Julia, we can use the same thing. We can call. First, we need to add the package. I already did. That's why it's commented out. Then by using, it's like import. This package is called pycall. We can, by using we import the pycall, and with this, within the pycall, we import Python library. So import this macro, because it's not a decorator, it's macro. This imports the request library, and now we can use it. So let's do this. Of course, we need to have request library installed in this virtual environment. or in this on this machine, but we do. So let's try and use it just like we used in Python. So let's get response with request.get. Yeah, it works. We have PyObject, something. No, looks nice. Let's access the status code. It doesn't work, but we can use this notation. This is indexing, and this object, I didn't talk about it. This is a symbol. It's similar to string, but it has one representation in memory, and it's used in metaprogramming, but it's also used in here or in other contexts. So we can get status code, we can get headers, we can even get dict of the object, Python dict. I mean, it's converted to Julia dict here. As we can see, this is a Julia dict with any and any. Those are types, the most generic type, and I won't talk about it today. But as you can see, it works. And if we print out the dict in Julia in Python, it will have the same objects. Those are PyObject here, because it all gets mapped to PyObject. This is an object provided by the PyCall library. Okay, so that's it. Maybe one bonus at the end. We can use LaTeX syntax to get special symbols in Julia and use them as names. This is very handy and very fun. We can use like sigma, delta, whatever, and they really work. How to do this? Use backslash. It's alpha. Now I hit tab. Now I hit tab second time, and I have alpha. Okay, let's get alpha. It looks like A, almost. So yeah, let's get Aleph. Aleph is 10. Should infinity. Okay, whatever. So it works. It works. So yeah, that's it. So thank you for listening. Stay tuned for my next talk about Julia type system and multiple dispatch. There might be 2 talks about it. Especially multiple dispatch is interesting thing. I didn't cover it at all, but it like turns over object-oriented programming on the head, and it's really interesting to know about those stuff. So thank you again, and see you next time.
Okay, I think we should just spend a few more minutes on some questions, because there are some on our chat. So thank you, Paweł, very much for a cool presentation today. And if you guys have any questions, you can ask them out on YouTube chat. Kamil has a lot of questions, so let's start with them. He says that he really likes IPDB in Python for debugging, and he asks if there is a similar solution for Julia.
Frankly, I didn't use Julia. I didn't use any debugger with Julia. I'm pretty sure there is one, because this is a dynamic language. I mean, it's compiled, but it's compiled on the run. So I think it's possible. It must be possible, but I don't know anything really about it.
Okay, so next question, also from Kamil, is Julia able to utilize a GPU? Like graphic processing unit?
Yeah. I'm pretty sure it does, but we would need to double check it. Also about computing capabilities of Julia, there are of course many libraries, but for specialized libraries. But the fun fact about Julia is that the vanilla Julia really is fast. So we don't need to use third type written in C or whatever libraries to achieve high performance. But about GPU, we would need to check.
Okay. And another question, which editors do you recommend for Julia development?
Yeah, this is the fun thing. I didn't check it, but the light table has some pretty fun Julia integration. It really shines. I mean, I saw it, but I didn't really check it. So light table and Julia, check it out. You will be pleased, I think.
And we also have some small discussion here because Piotr asks, what are the use cases that make Julia truly shine? He means, what can we do with Julia that we can't do with, for example, Rust or Go? But then so Kamil replies, so you can maybe say something more, because in Kamil's opinion, it's that maybe Rust and Go are designed to solve different problems. Rust memory safety, speed, systems programming, and Go maybe is for currency, networked apps. And is it possible to compare? So what is your opinion, Paweł?
Yeah, generally every fast programming language may be used for doing high performance operations. But Julia is specialized to please data scientists, let's say, or just scientists. You cannot really put a scientist on Go or Rust and make him or her happy. You cannot. They will be unhappy, and you would force them to write in Go, because Go is like almost like C, and C is extremely fast, but it's also very hard to learn, or it's not like the hardest language out there, but the language gets in the way. In case of Julia, it's Julia and type system and the syntax is based on both Python and MATLAB, and they are really like transparent for science people. So I think in terms of speed, it's like in first league, for like there's no doubt about it. And in terms of syntax, it's really better than those languages. And also, like Kamil said, Go is specialized for concurrency, and Rust for memory management. Julia does this as well, but it's not specialized for this. So possibly, in some cases, Julia won't be enough.
Okay, and I think there's one last question. Have you measured the Python integration performance-wise, and does it make Python run even slower, or is it acceptable?
I didn't test it, so like right now I would treat it as a gimmick, really, but maybe not. I think it may be used to like call, I don't know, plotting libraries in Python, but there are also already multiple plotting libraries in Julia, so it's also doesn't make sense, I think. But you can fall back to Python if you want to, like, yeah. But Julia is designed to avoid two-language problem, yeah, that you use one language to like prototype and do stuff, and the second language to when you have problems with performance. So ideally, maybe in the future, when the libraries of Julia, there are more and more libraries, this PyCall won't be used almost at all, because it's, yeah, but right now we can, but I don't know anything about performance. So yeah, of this.
Okay, great. I think that's those are all of the questions that we got. Maybe if there are any more questions, you can ask Paweł later, or if you just want to chat about new technologies or especially Julia language.
Yeah, I'm just checking my Twitter account.
Yeah, we can see.
Yeah, I know. So this is my Twitter. If you have any questions, I'd be glad to. Maybe I will copy it to this. I'll be glad to answer them. Second, let's make it. is my Twitter handle. So I needed to be sure.
Okay, I also put it on the chat here, so you can contact Paweł later. Okay, so thank you very much for joining us. Just for those of you who liked our today's tech talk, you can check our future ones on Facebook. Just follow our Facebook account, Sunscrapers, and we will inform you about any next presentations. And for sure, there will be a lot of them. And if you are interested in watching our previous one, you can go to our YouTube channel and check them. Have a nice evening. Thank you.
Yeah.
Bye.
Bye.